In this session, we're going to talk about word embeddings. These are what we are going to talk about in this session. First of all, I'm going to discuss the motivation of why we are concerned about word embeddings. Next, we're going to talk about what word vectors are and how we can train word vectors. And count-based methods are some types of mechanisms related to word vectors. And after that, we'll be having a look at how we evaluate word vectors. And then we're going to talk about word sentences and then summarize this session. Okay, first of all, the motivation of word vectors. As you can see here, there are numerous books, and these books contain knowledge from our ancestors and the concurrent knowledge. And from this session, we're going to talk about natural language processing, abbreviated as NLP. And what if we can learn all the knowledge in these books? That is the topic of NLP. And trained on text data, neural machine translation is quite good nowadays. As you can see here, you can use Google Translator and you can translate any language to another. And just 5 or 10 years ago, Google Translator was very poor. I mean, the performance of Google Translator was very poor. However, nowadays, the performance of Google Translator is above what we've expected. The performance is very good and the translation results are pretty accurate. And some of you might, I guess all of you have heard GPT-3. And this was a first step on the path to foundation models. This was developed by OpenAI, and you can do some dialogue with this machine. However, the very first machines, the algorithms, versions, were not that very powerful. However, as the ChatGPT came out, all the people now talk about large language models. This is a recent and intriguing set of capabilities. And this slide is from Stanford CS224N. And when you ask, hey, summarize Stanford CS224N NLP with deep learning, and ChatGPT already knows about this course and can summarize what this course is about. It's pretty amazing. And another thing is, you can convert Python dictionary into a latex table that uses book types. You can specify what package it should use when converting this Python dictionary into a latex table. And it does its job pretty well, quite well. And nowadays, many programmers are using ChatGPT for their work, not even for programmers. This ChatGPT passed Google's level 3 coding interview, although there are like level 9 in Google, but level 3 is quite good level for programmers. And another thing is, it also passed the bar exam of US lawyers. And this is like 1% of programmers, and this is like 1% of law studying students. Although it's not like 0.1%, but the performance is quite good. Okay, so you can do various jobs with ChatGPT. And this was one of NLP researchers' dream. And So from this session and for the next couple of sessions, we are going to talk about natural language processing. And when we start the journey of NLP, the first question that we need to ask is how do we represent the meaning of a word? Because a word is the basic meaning block when we compose a sentence or paragraph or a text. And what we want to do is represent the meaning of a word using computers. Therefore, we need to come up with a specific definition of meaning to represent words and meanings with digitized representations, like computer systems. And we're going to think about the definition of meaning from Webster Dictionary first. How does this dictionary define the meaning of meaning? The first definition is the idea that is represented by a word, phrase, etc. The second definition of meaning is the idea that a person wants to express by using words, signs, etc. And the third definition is the idea that is expressed in a work of writing, art, etc. Therefore, the meaning contains the idea. And the idea is in some way represented through words, phrases, signs, writings, art. Anyway, the meaning is the idea. And commonist linguistic way of thinking of meaning is like this: signifier and signified. In other words, symbol and the thing the symbol is indicating, signifying, idea or thing. This is sometimes called denotational semantics. This is an example. Here we have a symbol of tree, and there might be a concrete trees out there. This word tree might be indicating a concrete tree out there or some abstractional tree in our brain, in our mind. Okay, so the commonest linguistic way of thinking of meaning is signifier and signified, denoting something. And this is the very important question that we need to ask and answer. How do we have usable meaning in a computer? And previously, commonist NLP solution was using a thesaurus, for example, WordNet, containing lists of synonyms and hypernyms. Okay, what are synonyms and hypernyms? For example, the synonym sets containing good is like this: good, goodness, commodity, full, estimable, honorable, respectable, beneficial, upright, thoroughly, soundly, like this. As you can see here, this WordNet contains synonyms, meaning the words having similar or the same meaning as the word good. Now, what is hypernym? This is the hypernyms of panda. Panda is a carnivore or mammal. Panda is an animal. Panda is an organism. Panda is an object. Panda is a physical entity. Panda is an entity. So it is like a hierarchy between panda and other concepts. In another view, you can think of it as this diagram. There might be numerous objects connected to this node, and one of the objects is motor vehicle. And you can go down further and more specific object comes, for example, car. And car is not just one object that represents all kinds of car. Or car can be classified into SUV, compact, or hatchback, like this. Okay, so this is one example of hypernym. And are we satisfied with WordNet or thesaurus? Not at all. And what are some problems with resources like WordNet? This WordNet is very useful. However, it lacks nuance. What I mean by nuance is proficient, for example, is listed as a synonym for good. However, the thing is, this is only correct in some context. Therefore, depending on the context, proficient can replace good. However, in other contexts, it's not possible because they mean totally different thing. Also, WordNet lists offensive synonyms in some synonym sets without any coverage of the connotations or appropriate needs of words. Okay, this is one drawback of WordNet. And the second drawback is there might be some missing new meanings of words. For example, wisps, wicked, badass, nifty, wizard, genius, ninja, bombast. And these words are quite new, and some dictionaries don't contain these words. And it's impossible to keep up to date. And the definition of synonyms and hypernyms are quite subjective. Therefore, depending on who is categorizing the words, the result might be quite different. And of course, it requires a lot of human labor because there are like more than 50,000 or 500,000 words in commonly used English. Therefore, sorting out all the relations between words manually is not possible, feasible. And lastly, we can't use these WordNets with computers. Let's talk about the details in the following slide. Using WordNets, we need to represent words as discrete symbols. What do I mean by this is, in traditional NLP, we regard words as discrete symbols. Hotel, conference, motel, a localist representation. Such symbols for words can be represented by one-hot vectors. One-hot vectors means it contains only one element and the rest elements are zero. For example, you can signify motel as this vector and hotel as this vector. And this one signifies the index of this word hotel. And the vector dimension is the number of words in vocabulary. And it might be 500,000 or more. Therefore, even though the vector dimension is very high, it contains relatively very less information because only one element is one. And another problem is we can do anything useful with this type of representation. This is an example. In web search, if a user searches for Seattle motel, we would like to match documents containing Seattle hotel because motel and hotel are quite similar. However, when we represent words as these one-hot vectors, then these two vectors are orthogonal. There is no natural notion of similarity for one-hot vectors. And we can do nothing useful. And the solution might be try to rely on WordNet's list of synonyms to get similarity. However, it is very well known to fail badly because I told you that WordNet is subjective and it cannot contain all words. Instead, we could learn to encode similarity in the vectors themselves in an automatic way. And how can you do that? What we are going to do is representing words by their context. And this is sometimes called distributional semantics. A word's meaning is given by the words that frequently appear close by. And J.R. Firth is the first researcher came up with this distributional semantics idea. Quote, "You shall know a word by the company it keeps." This is one of the most successful ideas of modern statistical NLP. And when a word W appears in a text, its context is the set of words that appear nearby within a fixed size window. And we use the many contexts of W to build up a representation of W. For example, let's say banking is the word we are interested in. Then there might be many contexts that banking occurs. Then these context words will represent banking. Therefore, if banking comes frequently with crisis, then you might guess banking and crisis might have similar meanings. Or banking and regulation might have similar meanings. Or banking and system, a shot and the R, like these have similar meanings. Or crisis might have similar meanings as banking or happened. You can do the same for other words. Okay, up to this point, try to think about this question after pausing this video. Think about it on your own and let's check the answer together. Okay, let's check the answer together. The answer is the second one. Conventionally, researchers try to represent meaning in a computer through synonyms and hypernyms. For example, word, net. And the second option, representing words by their context words, is one of the conventional approach. No, it's one of the most successful modern statistical NLP technology. Okay, from now on, we're going to talk about word vectors. What are word vectors? We'll build a dense vector for each word chosen so that it is similar to vectors of words that appear in similar contexts, measuring similarity as the vector dot or scalar product. In contrast to discrete representation, such as one hot vector, what we are going to do is building a dense vector for each word. And how can you do that? So banking and monetary have similar meanings. And when we do a dot product between these two vectors, that might result in high value. That is what we are going to do. And word vectors are also called word embeddings or neural word representations. They are a distributed representation. And word meaning as a neural word vector, I'm going to show one example of visualization. Expect looks like this, and when you plot these words on 2D space, expect is here, and it is close to think. However, remain, become, be, are, is, were, as, was, are clustered. And words having similar word meaning are clustered in the same region. Okay, and what is Word2Vec? Word2Vec is a framework for learning word vectors. The idea is like this. We have a large corpus body of text. For example, Wikipedia or Yahoo News. They contain gigantic texts. And every word in a fixed vocabulary is represented by a vector. And this vector is called word vector. And how can you train these vectors? We go through each position T in the text, which has a center word C and context or outside words O. And we're going to use the similarity of the word vectors for C and O to calculate the probability of O given C, or vice versa. And keep adjusting the word vectors to maximize this probability. This is the basic idea. And let's have a look at the details. This is one example window and process for computing. Let's say we have the word into is currently the center vector. This is the center word at position T. And these are outside context words in window of size 2. If the window size is 3, then we're going to think about 3 words on the left and 3 words on the right. However, for this example, we're using the window size of 2 and outside context words in window of size 2. And what we are going to do is, given this center word, we want to increase the probability of the word t-1 given word at t. And we want to do the same for the word at t-2 given word t. And we want to do the same thing for the word t+1 given word t and t+2 given t. And the order or the position, whether it's on the left side or on the right side, doesn't matter. We just want to increase all the probabilities. And in the next step, now banking is the center word. And we are going to consider these context words and calculate these probabilities and increase these probabilities by modifying the word vectors. This is the basic idea. Then how do we train word vectors or learn word vectors? This is how I do. For each position T from 1 to large T, this is the length of the corpus we have. We are going to predict context words within a window of fixed size M. In the previous slide, I gave you the example of M equals 2, given center word WT. And the data likelihood can be calculated in this way. The likelihood is like this. These are parameters of our word vectors or our model. And we want to maximize for the likelihood of the context word given the center word. And this M changes from -M to M. This is the window size. In the previous example, I gave M was +2. So M goes from -2 to 2. And we don't think about J equals 0 because predicting the center word given center word does not make any sense. Okay, we are going to repeat this process for all the words in our corpus. And this theta is all variables to be optimized. These are word vectors. And the objective function j, theta, is the average negative log likelihood. Because I mentioned this several times, I remember. This multiplication, this probability is inherently less than 1, and multiplying multiple numbers that are all less than 1 will become easily 0. And we cannot optimize the word vectors. And what we can do is we take negative log to the likelihood, and we get negative log likelihood. And this multiplication becomes summation, and the optimization becomes more feasible. Okay? And minimizing this objective function is equivalent to maximizing predictive accuracy. This is the predictive accuracy, and this is objective function. Okay, so this was our objective function, negative log likelihood. And we want to minimize the objective function. And the question here you might have is, how do we calculate this probability? The answer is we're going to use 2 vectors per word W. One for when W is a center word, and the other for when W is a context word. Why do we use 2 vectors for one word? Because it's easier to optimize when we use 2 words. Then for center word C and a context word O, we are going to calculate the probability in this way. So this is a context vector, context word vector. And this is the center word vector. And because this is center, we use V. And because this is context, we use U. And this is for normalization. I'm going to talk about the detail why we need to normalize in this way in the following slide. Okay, example windows and process for computing this probability, just like this. In the previous example, this was the center word, and these are outside context words in window of size 2. And when you calculate the probability of U turning given into, you need to use U and V, because V is the center word, we use V here, and U here because turning is a context word. And for other words, we do this as before. So here we use U for banking and V for into. In other words, as follows. Okay, let's talk about this probability in more detail. This is the dot product between the context vector and the center vector. And this dot product compares similarity of O and C. And larger dot product means larger probability and higher similarity. And we are taking exponentiation to make anything positive, because we want probability, and probability cannot be negative. That's why we are taking exponential here. And this term normalizes over entire vocabulary to give probability distribution. So this is done for every word in the vocabulary. Let's say our vocabulary contains 500,000 words. Then we need to repeat this process for 500,000 words. And this is an example of the softmax function, mapping from Rn, R to the power of n, to 0, 1. And the softmax function maps arbitrary values to a probability distribution P. And max, because it amplifies probability of the largest element. And soft, because still assigns some probability to smaller elements. And frequently used in deep learning, we already saw this in the previous sessions. Okay, that was about the definition of word vectors. And from now on, let's see how we can actually train word vectors. And we know how we optimize some neural network and this word vectors. To train a model, we gradually adjust parameters to minimize the loss. And recall that theta represents all the model parameters in one long vector. And in our case, let's say our word vectors are d-dimensional and v many words. And remember, every word has two vectors. Therefore, our parameters are like this. All the v's for standard words and all the u's for context words. And because each vector has a dimension of d, and we have two sets of these vectors, we have 2 here, d here, and we have v number of words, 500,000 words. And we optimize these parameters by walking down the gradient. We know how we can do this. And we compute all vector gradients. That's what we're going to do. And we know how we derive this gradient. And the basic Lego piece is the chain rule. We know what chain rule is. If in doubt, write it out with indices. Useful basic fact is when you derive this vector dot product in respect of x, it results in A. And even though we change the order of the dot product, the result is the same. You can remember this basic fact. And let's think about chain rule first. If y is fu and u is gx, so this is equivalent to y equals gx, like this. And when you want to derive y in respect of x, you first need to derive y in respect of u, because y is represented as u. And next, you need to derive u in respect of x, like this. And this is our example. Now, when you want to derive this one, we first need to derive this one regarding x cubed plus 7 as u. And it becomes 5 times u to the power of 4. And when you derive this, it becomes, in respect of u, it becomes 20 times u cubed. And the next step is u is gx, which is x cubed plus 7. When you derive this in respect of x, it becomes 3 times x squared. And you multiply this one to this one. So dy dx, which is dy du dx, is 20 times x cubed plus 7 squared times 3 times x squared. Okay, this is very simple. And our objective function looked like this, and our probability looks like this. And we need to calculate the gradient for the standard word. We need to derive this term in respect of the standard vector. And after calculating this gradient, we can use this gradient to update the standard word vector by multiplying some learning rate like this. That's the basic idea. And let's derive the word vec. This was the objective function. And how do you derive this one? First, this one is ratio. And ratio is not good for derivation because it complicates the computation. And because we have log here, we can divide this division into two terms, like minus subtraction. And because we have log here and exponentiation here, they cancel each other. So they are canceled, and we get U sub O transpose times V sub C. And we already saw how we can derive this term very easily. This was just simply UO. And when we come to this point, it is somewhat tricky. However, when you derive log x, we know it is 1 over x. And because this is x, it goes to the numerator, denominator. I'm confused. Anyway, the bottom side like this. And we need to derive this one once again to apply the chain rule. So here we're deriving U is okay. So this is U. And we cannot derive this one directly. So what we're going to do is U log U. And then we're going to multiply this one, okay? So when we calculate this part, it becomes U over 1. B 0. This is U. And U was this exponentiation, this one. So we're putting U here, okay? So U goes here, and these vectors are independent. So you can put this derivation operator inside this summation like this, okay? And we know that this fact, and because this one contains some tricky value, we're going to substitute and apply chain rule again. And we know deriving this vector product in respect of VC is UX. So we're just putting UX here. For some of you who do not remember this fact, think about this useful basic fact. Okay, and we're going to put this division into this summation again. Because this is a constant, it is okay to put this inside this summation. And what is this? We saw this in the previous slide. It was the probability, right? So this is the probability of X given C. And the word or the expectation. So this is the probability of observing vector X, word X, given the context, given the sentence word C. And this is a weighted summation. So it is a expected vector. And this is actually observed vector. As you can see here, the gradient is just the difference between the observed and the expected. This is quite intuitive, right? Okay, we have calculated all gradients to train word vectors. We went through the gradient for each center vector v in a window, and we also need to calculate the gradients for outside vectors u. And the process is quite similar, and you can do it on your own. Generally, in each window, we'll compute updates for all parameters that are being used in that window. Okay, this is another visualization of learned word vectors. Similar words are clustered in a similar region, like Tuesday, Christmas, like this. Okay, we are going to see how we can implement this one in the implementation session. Okay, let's talk about more details. Why do we learn two vectors rather than one? Because it is easier to optimize. We are going to average both at the end. And two model variants. The first one is called skipgrams. We predict context words or outside words given center word. We don't care about the position, whether it's on the right side or left side. We don't care. The second one is called continuous backup words, abbreviated as CBOW. We predict center word from backup context words. So given context words, we are predicting the center word. And in the case of skipgram, we're just given the center word, and we want to predict these context words. Because we can easily see that this task is easier than this one, so it might take longer to learn skipgrams. And this lecture so far talked about skipgram model. And we can pursue additional efficiency in training. The first one is called negative sampling. And so far we focused on naive softmax. It is simpler to implement. However, it is quite expensive because we need to calculate this summation over and over again. So we need to calculate this one over and over again. And this part is quite costly. So this is the repetition of what I told you in the previous slide. The normalization term is computationally very expensive, this one. Hence, in standard word2vec, you implement the skipgram model with negative sampling. The main idea is like this. Rather than training this softmax, we're going to train binary logistic regression for a true pair, center word and a word in its context window, versus several noise pairs, the center word paired with a random word. And the job is given the center word and a word in its context window. This model should output 1. However, when it is given several noise pairs, like the center word paired with random word, it will just produce 0. So it's called binary logistic regression. Rather than learning this expensive probability, this one approximates this process. From this paper, we're going to talk about negative sampling. The overall objective function with negative sampling is like this. We want to maximize the probability of the context word and the center word, sigmoid. And for negative samples, we want to minimize the probability. Okay, so this is going to be the overall objective function. And we take k negative samples using word probabilities. How do you sample these negative samples? According to the word probabilities. It maximizes probability that real outside word appears and minimizes probability that random words appear around center word. And sample with this probability. This is the probability of each word to the power of 3/4, because the unigram distribution raised to 3/4 power. This makes less frequent words be sampled more often. So it balances the frequency. All right. We iteratively take gradients at each window for SGD, and each window we only have at most 2n+1 words plus 2km negative words with negative sampling. And what this means is the gradient is very sparse. Other words not in the window at the moment will be 0. And only the words in our window will have some values in their locations. Therefore, this gradient is very, very sparse, and handling this gradient all the time is very inefficient. We might only update the word vectors that actually appear in our window. And the solution is either you need sparse matrix update operations to only update certain rows of full embedding matrices U and V, or you just keep around a hash for word vectors. If you have millions of word vectors and do distributed computing, it is important not have to send gigantic updates around. Okay, so what we are going to do is we only think about these parts as hashes. So we are not going to construct this gigantic sparse matrix, but we are going to just have this hash or list of gradients like this that only have some values. You also need to keep track of the ID of these words. And we are going to update only that part. Okay. So think about this question to summarize what we've discussed on your own after pausing this video. Okay, let's check the answer together. The answer is the first option. Word vectors are not discrete. They are dense representations of words. And word vectors are also called embeddings or word representations. And training word vectors typically requires a large corpus, and scriptgrams predict context words given the center word. And CBOW predict the center word given the context word. Okay, from now on, let's talk about count-based methods. Up to this point, we wanted to learn the co-occurrence of words. Then you might ask, why not just capture co-occurrence count directly? And there's something weird about iterating through the whole corpus, perhaps many times. Why don't we just accumulate all the statistics of what words appear near each other? And this is by building a co-occurrence matrix X. There are two options. First one is window-based, and the second one is full document. Window-based is similar to word fact. Use window around each word and capture some syntactic and semantic information. And Word document co-occurrence matrix will give general topics. All sports terms will have similar entries leading to latent semantic analysis. Document space. So it's like word space and document space. Okay, for example, let's say we have just window length of 1, and this is symmetry, irrelevant whether left or right context. An example corpus is I like deep learning, I like NLP, I enjoy flying. Then we're going to list all the words in our vocabulary on this row and column like this. And I and like co-occurred 2 times, and I enjoy co-occur just one time, like this. And this matrix is inherently symmetric. So the co-occurrence matrix is a symmetric matrix. This 2 has 2 here, 1 here, like this. It is very simple. You just need to count the co-occurrence of words. And this simple count co-occurrence vectors increase in size with vocabulary. And it's going to be very high dimensional, require a lot of storage, though sparse. And subsequent classification models have sparsity issues. Models are not robust. And we want low dimensional vectors. That's why word vectors came out. And another thing we can do with co-occurrence matrix is store most of the important information in a fixed small number of dimensions by constructing a dense vector. Usually 25 to 1,000 dimensions, similar to word vector. And how do we reduce the dimensionality? How do we reduce the dimension? We basically use singular value decomposition, factorizes x into u sigma v transpose, where u and v are orthonormal. So it looks like this. This is basically a square matrix, but this is for general SVD. And what we're going to do is retain only k singular values, 25 or 1,000 dimension, in order to generalize. And M is the best rank k approximation to x. However, computing singular value decomposition is very expensive. And what I mean by retaining only k single value is like this. In this case, we only retain 2 values. So originally it was 4 dimension, but it becomes 2 dimension. And we keep only 2 singular values, here 2 dimensions like this. And another problem is we need to scale the counts because the functional words like the, he, has are too frequent and syntax has too much impact. So we need to introduce some fixes. We can log the frequencies or cap the count with 100, or we could ignore the function words. And we can use ramped windows that count closer words more than further away words. Or we could use Pearson correlations instead of counts, then set negative values to 0. And another thing we can do, rather than Pearson correlation, is point-wise mutual information, PMI. What we can do is, PMI is like this. The definition of PMI is the mutual information, the co-occurrence probability divided by the probability of each vector. And because when we calculate this probability, we need to normalize this value with total number of n, and we can just ignore, cancel out these two n's. And we have n as vector, how many times these words are occurring. And because we consider these numbers, actual counts in our calculation, the PMI between the and car is 2.32, and the PMI between car and drive is 7.97. So this is higher. And although this word is quite frequent, and the co-occurrence between the and car should be more than the co-occurrence between car and drive. However, the PMI is what we expected. This is higher, okay? This is because normalization. And we sometimes use positive PMI because PMI could become negative and we don't want negative values. And interesting semantic patterns emerge in the scaled vectors. So drive, driver, swim, swimmer, teach, teacher, marry, priest, like this. And up to this point, we've discussed two approaches, count-based and direct prediction. And this is the family of direct prediction, and this is the family of count-based. This one is fast and efficient because it uses statistics. However, direct prediction scales with corpus size, so it becomes slower as the corpus size increases, and it does not use the statistics that much. However, it generates improved performance on other tasks. However, it can only do capturing similarity. It can do no other jobs. And this can capture complex patterns beyond word similarities. However, this is disproportionate importance given to large counts. Okay, and another point I want to make here is the ratio sometimes gives very important information for us. So here you can see given ice, the solid probability is quite high, the water high, but gas and random is low. And steam, water is large, gas is large. So small, small, large, large, give some information like this. And when we actually put real numbers, it goes like this. And we sometimes want to encode this information in our word vectors. How can you do that? How can you capture ratios of co-occurrence probabilities as linear meaning components in a word vector space, embedding ratios of co-occurrence probabilities? We could use log bilinear model. So given the word J, we want to predict the probability of I. We do just dot product between these two word vectors. And with vector differences, we do this. So for ratios, we calculate the subtraction between these two vectors. That's all, okay? All right, and Glove combines the best of both worlds, count-based and direct prediction. It is fast and scalable to huge corpora, and it shows good performance even with small corpus and small vectors. And this is the result. These are very difficult words, but Glove captures the meaning of these words very well. Okay, think about this question on your own after pausing this video, and let's check the answer together. All right, the answer is the fourth one. Count-based co-occurrence matrices contain high-dimensional word vectors. That's why we wanted to use SVD to reduce the dimension. And singular value decomposition is computationally efficient? No, it's very expensive. And point-wise mutual information output, it can also output negative values. That's why we are using PPMI, positive PMI. And learning the statistics of co-occurrence is similar to constructing a co-occurrence matrix. So they are doing basically the same thing. Okay, up to this point, we have discussed how we learn word vectors through two approaches. The first one was count-based, and the second one was direct prediction. And after learning those word vectors, how can you evaluate whether they are good word vectors or bad ones? Okay, related to general evaluation in NLP, intrinsic versus extrinsic. Intrinsic means evaluation on a specific intermediate subtask. It is fast to compute and helps to understand the system. And not clear if really helpful unless correlation to real task is established. Because we are just evaluating on a specific and intermediate subtask. On the other hand, extrinsic tasks are like this: evaluation on a real task and can take a long time because we need to implement the whole system. And unclear if the subsystem is the problem or its interaction or other subsystems. If replacing exactly one subsystem with another improves accuracy, then good story. Okay, one of the most famous intrinsic word vector evaluation protocols is word vector analogies. Given man and woman and king, what will be the word here? We know that it should be queen. This is evaluating word vectors by how well their cosine distance after addition captures intuitive semantic and syntactic analogy questions. The problem is, what if the information is there, but not linear? This word vector analogies assumes that the relations are linear. And you can do some Korean word vector things. And when you subtract Seoul from Hanguk, Korea, and add Tokyo, then it will show you Ilbon. It is intuitively correct. Another intrinsic word vector evaluation is human judgment. There is an example data set. Humans judge tiger and cat are 7.35 similar, and tiger, 10 point similar. And we are going to evaluate whether our learned word vectors display outputs the same similarity as humans. However, this is quite subjective, right? And one extrinsic word vector evaluation is called named entity recognition. We're going to use word vectors to perform named entity recognition. And what is named entity recognition? NER. This is given a sentence, we want to recognize or classify the entity of the names. This is the name of a person. This is the name of an organization. This is the name of place, an organization like this. If our learned word vectors improves the performance of this named entity recognition system, then we can conclude that our word vectors are quite good. Okay, another issue is most words have lots of meanings, especially common words and common words that exist for a long time, like pike. And here you might question, does one vector capture all these meanings or do we have a mess? Like pike has so many different meanings like this. And there are numerous research efforts to resolve this issue. Some try to resolve this issue by learning several word vectors for the same word, jaguar, like this. Here we have jaguar 1, jaguar 2, jaguar 4, jaguar 2 here, jaguar 3, like this. And this is an ongoing research topic. Okay, let's summarize this lecture session. Today we talked about the motivation of word vectors. We wanted a dense or discrete representation of meaning to process language with computers. And we discussed how we train word vectors, direct prediction or count-based. And we had a look at how we evaluate word vectors. There were intrinsic versus extrinsic. It took longer time for implementing extrinsic tasks. However, it is more intuitive. And intrinsic deals with sub and intermediate tasks. And we introduced some future research directions like word senses. Okay, this is the end of this video. And from next video, we are going to actually implement the ideas discussed in this slide.